Well, a good morning to everyone that has just joined us, and hello to everyone that's watching the replay. Welcome to another one of our online learning webinars. This time it's all about wet happens, dealing with it in modern timber buildings. I'm your host, Andy Ferguson, and today, for the first time, we have two guest presenters, two experts on. I just want to quickly introduce both Dr. John Williams, Principal Consultant at RSK, and James Walker, Technical Director of Miller Associates. We are about to start the main presentation. For those that have just joined us, just very quickly, if you do want to pose a question over the course of the webinar, if I can point you over towards the chat facility, if your desktop will either be in the left or the right hand side. If it's in a mobile device, you just may need to kind of pull up and you'll see it there. Feel free to tell us where you are in the world and what it's like. And again, any questions there. Also, if you do have any questions over the course of the webinar, just simply email me at andy@property-care.org. That's andy@property-care.org. Similar, if you are watching the replay of this, please do use that email address. I will try to endeavour to answer any questions that you may pose if you are watching the replay and forward them on. Well, John, James, it looks like we are pretty much almost there for the main event. So if I kind of summarise just for our audience, as much, I suppose, as we like to try and minimise the risk with timber wood, it is inevitable that sometimes modern timber just simply gets wet. Modern timber will then need to be surveyed, maintained, repaired from time to time. Things like CLT, cross-laminated timber, and other forms of modern timber framing is something that certainly I know the PCA, especially both my CEO, Steve Hodgson, and our technical director, James, has been looking into certainly over the past years and extensively recently. We have been trying to keep up to speed on this. It's part of the reason why it led to this particular webinar ourselves. And I know many of our listeners are wanting to get up to speed on it as well. But what are the key challenges of measuring moisture and assessing decay in timber in buildings? And what tidbits, I suppose, can you guys really pass over to the many of us? I suppose in that point, it's really a case of passing it over to yourselves.
Thank you. Good morning. So the working title for this in true tabloid style was Water Kills Timber, but I was asked to perhaps adopt a more broadsheet approach with the title. We're going to cover quite a lot of ground over the next 40 minutes, so the delivery of this talk will be quite pacey, and we're going to be adopting the rules of the BBC Radio 4 panel show just a minute. Where there is any deviation, hesitation or repetition, we're going to move swiftly on to the next slide. As you can see here, there's quite a lot of subject matter. We're going to be looking at the different types of timber product, engineered timbers, which we use for construction. We'll be talking a little bit about water getting into buildings during the construction phase, what can happen during the occupation phase if there's a lack of intervention when there's water inside our building, and more importantly, we'll be looking at the effect of decay on the strength and integrity of these products, and what engineering interventions may be required, or what remedial strategies in terms of treatments we can employ. And the pictures on the right you can see here show a range of water damaged materials. So here, for example, you can see the water getting in. I'm going to ignore that, it's not working, bear with me. So the pictures on the right just show you a range of different types of timber materials that have been damaged by exposure to water. And the one on the bottom left is an oriented strand board panel that's been turned into Weetabix due to long-term wetting. In the UK, we have a temperate maritime climate, which means it rains a lot. So the picture on the left gives you a flavour of the typical weather fronts we're bombarded by over the course of the year. So I originally come from West Wales, so it's like living in a washing machine there. And as it's March, anyone else from West Wales will realise we've just come out of spin cycle. But more importantly is the picture on the right, which has been taken from the Met Office data, and it shows the increase of rainfall in December 2020 when it's compared to the average rainfall for the period 1980 to 81 to 2010. And as you can see by that blue shading, over time, there has been a substantial increase in rainfall hitting our country. And what this means is the risks associated with exposure to increasing rainfall are going to get worse. And this is as a consequence of climate change. So it's something which the construction industry ought to be considering and factoring in, particularly if we're building more and more buildings with timber materials. So moisture control should be a priority during construction. Certainly in my experience, I think this seems to be a bit of an afterthought. And if you've got any views on this, put them into the chat. It'd be interesting to hear your opinions on this. So how do we control moisture? Well, we can build when the weather is dry and sunny, but clearly in a maritime climate, that's not going to happen. So we're faced with this perennial risk. There is a perception that moisture penetration can be ameliorated once the roof is up. So get the roof over the building, it will dry out quickly. Not always the case. As you can see in the picture here, we've got quite a lot of standing water on the deck of this cross-laminated timber building with the roof on. More importantly, with mass timber buildings, there is more timber, which means it can hold more water that acts as a reservoir, as opposed to a standard stick-built timber frame building. And just to give you an example, if we look at a flat roof of about 100 square meters, which is about 2 tennis courts, if we have a period of heavy rainfall lasting for 10 hours, which these days is not unusual given the changing rainfall patterns we're experiencing, that's the equivalent to 8 tons of water landing on that roof. Now, clearly it doesn't stand there, it disperses. But where does this water go and what can it do? Well, it pretty much gets everywhere, aided by gravity to get into your building, or be discharged down the sides. This is an interesting slide from colleagues I work with in the States. They sent me this. It's a computerized tomography picture of a cross-laminated Douglas fir panel, and it's showing the wetting. The picture on the left of your screen is showing you a dry panel, and the picture on the right, indicated by the red arrows, is showing where the water gets in after exposure. And once the water gets into these joints, it's very difficult to get it out. And we're faced with what we can have in the worst case example is a deterioration continuum, where the small picture on the left shows you what can happen to a mass timber panel when it's exposed to the weather and it dries out. We can get some shrinkage, and this causes the butt joints to open up. Then it begins to rain, and these butt joints allow quite a lot of wetting to develop, and then we can end up with quite a potential risk of decay if that water isn't removed from the cross-laminated timber panel. When does moisture ingress occur? Well, at the top of the slide, you see some various points during the life of a timber product, from manufacturing right the way through to in service. And you can see that the biggest risk we've got is really construction moisture. After the building's completed, then we've got other risks associated with the pernicious leaking pipe, a plumbing failure. Also, we could have some inbuilt deficiencies in the design of the building. We could have condensate. We could have a build-up of condensation. The picture to the bottom right of your screen, the sort of shiny appearance there is condensation forming around a poorly lagged pipe. Over the course of time, this can present a decay risk. The 3 pictures to the left show an interesting illustration of what can happen when water gets into the end grains of a solid piece of timber. Over a period of 7 days, you can see it's a bit like a school chromatography experiment. We can see quite a lot of substantial wetting at the base of the panel here. This can have two causes. Number one, the swelling of the timber can cause a loss of cohesion in the adhesive bonds if we're dealing with an engineered product. And secondly, again, if that water isn't removed, we end up with a substantial decay risk. And this decay is occurring just where we don't want it to occur. It'll be developing around where the fixings are. So how do these different materials perform when they're exposed to wetting? Well, most of our engineered timber products derive from softwoods, mainly European whitewood. It's an abundant material, and it's pretty good for construction. And the great advantage of this is we can either use it as solid timber, or we can take what could be arguably described as a poor quality product, remove all the defects, cut out the knots, and come up with engineered products such as the flanges for I-beams, or glue laminated timber, or cross laminated timber. Now, the problem with European whitewood, whitewood and most other construction softwoods, there's little resistance to decay. Also, wetting can, like all timbers, wetting can affect the mechanical properties. Wet timber is not as strong as dry timber, and in certain cases we can have a loss of fixity as well, which can put stress on our connections. Also, swelling, as I mentioned earlier, can cause bond disruption and loss of cohesion, particularly in panel products such as oriented strand board. Referring back to the previous slide, if we have rapid drying, that can lead to the development of internal stresses, which opens up the material. If you're then exposed to subsequent wetting, then these openings do act as moisture superhighways. The water can get into the product and penetrate quite far and penetrate quite deeply into the material. So at this point, I'm beginning to lose my train of thought, and with the Radio 4 theme in mind, I'm quickly sounding as if I belong. I'm sorry, I haven't got a clue. And at this point, I'm going to hand over to James.
Great, thank you, John. And so following on from what John was starting to explain in his last slide, there are actually a number of different timber products. When we say timber, it's actually a family of products that we're referring to, all derived from trees. But depending what we do with those logs in the first instance, then we can form different timber products. And the first thing that we can do is we can cut it into rectangular sections and form our sawn timber elements, the 2x4, commonly the C16, C24 grades. And we can build directly with those timber elements. The limitation is that, the size of the tree is limited. And so we can only build with the sizes of timber that's available from the tree. And so there are methods to actually increase the size of the timber section. And so we can laminate it using nails or by using adhesives. And so we can nail laminate the timber or glue laminate the timber to create glue lam. And if we bond it all together with the grain orientation in the same direction, we can create beam or column type elements. Or if we can laminate it in alternate directions to create panel type elements, and that's cross-laminated timber. There are a huge number of different varieties. If you're interested in particular forms, then feel free to post some questions in the chat. We'll be happy to answer. The other thing that you can do with a log is you can actually peel the log and create veneers or plies. And then once you've got those veneers, you can start to make products like plywood by bonding together successive layers. Again, if you orientate the grain in different directions, you can create plywood, or if you have them all in the same direction, you can build up bigger sections to create beams and columns with laminated veneer lumber. The other thing that you can do is with the waste products, with chips and particles, you can create particle board or oriented strand board, OSB. There's so many different acronyms like in any industry. But yeah, if you've got any questions, put them in the chat. And the point really is that all of these different materials will respond slightly differently to moisture, and the presence of absence of adhesive will mean their behavior is different if they get wet. So now I'm going to be talking a little bit about the different forms of timber construction, and perhaps the most basic form is the sort of open panel. Where buildings are built on site, that's usually referred to as stick built with timber elements. But more commonly now in the UK, the panels are actually built in factories and then brought to site. And in its most basic form, it's known as open panel construction. And that's because the wall stud elements and the floor joisted elements are built up as panels with the deck and the sheathing board to give it some rigidity and stability. And then the whole building, whatever shape and size, is assembled on site. Now, these ones, if you get construction moisture, is usually quite easy to see. A little bit of wetting is fine. The timber can take some wetting over a period of time. The key thing is to dry it out. And these buildings are quite easy to dry out because they're open and exposed, and the timber's exposed. What's becoming more popular in the UK now is closed panel construction. That's a little bit more advanced than the open panel construction, where you do more in the factory. You actually insulate between the studs, put plasterboard linings on, and then also maybe even do windows and doors. And you get the benefits in quality assurance and process improvements from those methods. And then all those panels are brought to the construction site and they're assembled together using a crane. Now, as you can probably imagine, if there's moisture that gets into those panels, it's quite hard to detect, and then it's hard to dry them out as well. So you need a good moisture control plan to actually avoid moisture getting into those panels in the first place. Then we move on to construction using structural insulated panels, otherwise known as SIPs. And these are structural panels that have a foam core, so very good for insulation. And they have structural facing panels on both sides. In this case, in the photo on the right-hand side, you can see oriented strand board OSB facing material. Now, because there's quite a thin structural element, if these get wet, again, a little bit of wetting is okay. But if left for prolonged periods of time, that can start to become a problem. So again, because like the closed panel, if these get wet, it's quite hard to detect and can be difficult to dry out if they're covered up. And then obviously if they're covered up, it can be quite difficult to repair. And we have a sort of cross-laminated timber construction that's more modern, although it has been used for the last sort of 20, 30 years. And the nice thing about cross-laminated timber is it comes in big panelized forms. So you can get up to 350 millimeters thick by about 3.5 meters wide by about 16 meters long or more. And you can build up a building very quickly. It's very strong so that you can build tall multi-story timber buildings. There's a bit of a race around the world going on to see who can build the tallest timber building. This one is in Norway and stands at 49 meters tall. You can also process things like windows and doors. But again, because of the panelized construction, if you get moisture into the gaps and joints, it can be quite hard to detect the moisture. And because it's large timber sections, it takes a little longer to dry out and it can be quite difficult to repair. But no different methods than other forms of construction. So we're going to talk a little bit about wood as structural material here, and it's a useful analogy to think of wood as a bundle of straws. And then by visualizing the bundle of straws, we can understand a little bit more about the properties. Now, processed wood is called timber for structural applications. So wood is what you would throw on your fire for warmth, whereas you would build a building out of timber. And if we think to our bundle of straws analogy, the timber is very strong parallel to the grain, but weak perpendicular to the grain. And those tubes in the structure of the wood are actually used to transport moisture around the tree, transport water and nutrients and sugars. But then once the timber is processed, those same tubes can actually migrate moisture. So in any timber building, we need to pay particular attention to the end grain of the timber, because that can really draw moisture. And after felling of the tree, the timber is known as green wood and it's full of water. And if we look at that in a little bit more detail, we can see that after felling, all of the sort of voids between the fibers are actually full of water. And green wood is around 100% moisture content, more or less. But then as the timber dries out, those voids release the water, and the only moisture that's left in the timber is within the fibers themselves. And that's typically about 25 moisture content, which is known as fiber saturation point. And you can see on the graph on the left that between 25% and 100%, there's no change in the strength of the timber. But below 25%, the strength of the timber increases rapidly. So it's really important to keep the timber below 25 or at a low level. Typically in service, it's about sort of 10% moisture content. The fibre saturation point is also an important metric in that anything above about 25% plus or minus would start to become at risk of decay. Moisture in timber is not the only thing that can reduce the strength. Obviously, if the moisture is left for prolonged periods of time and you start to get fungal decay, then the strength of the timber will also reduce as the fungus breaks down the fibers of the timber. And there's a graph on the left there showing how a brown rot decay would reduce the strength of a pine timber, and in terms of its weight, its strength, and its stiffness. So it's really important that we try and keep timber dry at all times. And so now I'm going to pass back over to John, who's going to talk a little bit more about durability and how to detect if your timber is starting to decay. So over to you, John.
Thank you, James. So what do we mean by natural durability? Well, it's the resistance of the timber to decay. However, this only applies to the heartwood. The sapwood of all timber species is classified as not durable. And the bad news here is we use a lot of European whitewood for our structural timber. It comes from plantation forests. It has a high proportion of sapwood, so it has very low resistance to decay. And also the heartwood, the core of the timber, has very poor resistance to decay. So to stop it rotting, we need to keep it dry, or we need to protect it with preservative treatment. Whitewood is also quite difficult to treat as well. So that's the bad news. Is there any good news? Well, yes, there is. So if we look at the service situation and the risks of decay, if there's an increasing risk of wetting, then there's a corresponding increasing risk of decay. When we're dealing with our timber frame buildings, we're going to be in use class 1, where it's interior and dry and there's no risk of decay. On a worst case scenario, we could have a poorly ventilated ground floor or a cold roof where the timber could become occasionally wet due to build-up of relative humidity, and we could get short periods of wetting, which could present a decay risk. So a well-designed building should not experience any decay. What conditions are needed? Well, for your living organisms, like you, they need warmth and they need food, and also they need moisture. Now, the industry states 20% moisture content as the decay threshold for prolonged periods. That takes into account some slight inaccuracies with moisture meters and a little bit of a safety margin as well, because surveyors don't like to be sued. In reality, the decay really starts to take hold between about 24, 25, 26 moisture content. The optimum range is about 60 to 80%, and that's heavily influenced by temperature as well. So the warmer the temperature, the more active the decay fungi. Now, add some comments on your views on this. Now, for decay to develop, or for the spores to germinate and to grow in the timber, you need wet conditions for weeks, possibly up to months, for the decay to initiate, and even up to a year. In my experience, I've seen modern timber frame buildings suffer quite severe decay within a 12-month period. On the same point, I've had a lump of glulam outside of my garden for more than 8 years, and it's still doing okay. So there's no hard and fast rule as to how long does it take for a wet piece of timber to begin to decay. The important thing is it doesn't take days, it doesn't take weeks. It takes quite a few weeks, probably months, sometimes up to a year or possibly longer. So the best strategy is to keep the building dry. Don't let it get wet in the first place, and to minimize the exposure to construction moisture, but not always possible. So what types of decay are there? Well, wood is just a matrix of complex sugars glued together with lignin. There are brown rot type decay, which favor softwoods, and there are white rots, which favor hardwoods, although they can also attack softwoods. So in the main, we're looking at brown rots. You need to keep your eyes out for dry rot, circular lacrymans. It's a little bit more pernicious than other wet rot type fungi, and that's because it's evolved to take advantage of, let's say, marginal conditions where you've got perhaps a lower moisture content in the timber, but high relative humidity. What you do find, though, in these sort of conditions is the dry rot will travel across the timber and take advantage of moisture in the boundary zone, in the surface, but it may not penetrate deep into the timber because there isn't enough moisture deep within the timber to support growth. I've rarely seen damage caused by wood-destroying insects in a modern timber building. Plenty of insect damage in older buildings, but not in modern timber buildings. So again, I'm just one person. If any of you out there are surveyors who've seen some significant insect damage in modern buildings, we'd be interested to hear from that. So what do we need to look for? When do we use decay detection drilling? What can it tell us? When do we open up? And what are the risks we're facing with? So I'm not going to list what's on the left-hand side of the slide. I'm slightly conscious of time here. But the key issue is, where is the water going to cause the damage? Now, hopefully this will work this time. So the sole plate and also the lower section of the oriented strand board. So this is in a standard open frame, open panel timber frame building. Where the wetting is most evident on the sole plate, we may find some decay here. We may find some water damage and debonding of the oriented strand board at the base of the panel. And that's quite serious because that will affect the racking resistance of the panel and ultimately the stability of the building. You can also see as quite a serious problem with mold here. So that's another issue which needs to be dealt with and outside the subject of this talk, really. If we go back to mass timber, which is of primary interest, we've got a vertical wall panel sat on the horizontal floor panel. When the water gets into the building during the construction phase, it's going to accumulate at the junction. And that's just why we don't want the water to accumulate, because where the timber gets wet, as we can see in this highlighted area, not only will it lose some of its strength and fixity due to the fact the moisture content has increased, but it's also vulnerable to decay. So we've got two modes of failure occurring in the most critical part of the structure. So this is where we need to be focusing our surveys. This is an example of some typical wetting we'll see in an open panel timber frame house. Fairly easy to dry out because we can get plenty of air movement through the building and we can pretty much see the damage. Also, because we're dealing with stick frame, we've got quite a large surface area to volume ratio, so we can get, so there's not an awful lot of mass for that water to wet up. In contrast, if we're dealing with cross-laminated timber buildings, then we have a much smaller to volume ratio, which means the panel can hold a lot more water and there isn't as much airflow. So when we're carrying out a survey, we want to look at the moisture content in the points which are at most risk. And on this slide here, you can quite clearly see the tide marks where the water has got in at the edges and it's traveled up the panel. So this is where we're going to be testing the integrity of the timber using decay detection drilling. It's also where we're going to be testing for moisture content. And we can track back. So around about this area, we'd expect to see some high timber moisture contents. And as we move out away from the wall, we'd expect the moisture contents to drop off. So if I was doing this inspection, I would probably take a few reference readings where I know there isn't any wetting, just to see what the equilibrium moisture content is. And I'd also be testing at different depths as well, just to make sure I wasn't getting any interference from the glue lines, which can affect the readings. This is an example of some decay observed in the roof panel of a cross-laminated timber building. So there is some research to show that even a modest weight loss in the timber can cause up to a 50% loss of strength. And this is right at the bearing point and also where the connections are going to be present. So again, in the chat, what do you think? What type of fungus is that? You don't really, as a surveyor, I don't think, in my opinion, you don't really need to identify the precise species of the wet rot fungus causing the damage. You just need to know where it is in the building, how much damage it's caused, and is it still active? But anyway, bit of fun. See if you can identify the species. Let us know what you think in the chat. So these series of photos here, these two photos, the one of the insert, this is showing the typical damage we can expect to see in mass timber. The surface is quite grey, so it's clearly been exposed to sunlight in the past. When we lift it out of laminates, you can quite clearly see the fungal mycelium underneath. And if we focus here, you can see the timber has cracked and opened up. So if I was going to stick a screwdriver into that, I'd probably be able to dig out quite a lot of decayed timber. This is the decay, this is the progression of more decay. So I'm not going to dwell on this. Quite clearly, you can see here that if undetected for long periods of time, you can end up with some serious obliteration of your structural timber. So decay detection drilling. I like to use two methods. I like to use wood augers about 6 mm in diameter, as you can see on the left. They do leave some holes in the structure, but the advantage is not only can I see the condition of the drill arisings as they come out, but I can also put in some insulated probes to measure the moisture content at depth through the timber. The apparatus on the right, this is a resistor graph, takes away the operator subjectivity. So it's basically a case of man versus machine, where the machine does the drilling for you. But interestingly, it gives you a computer printout where you can see the printout tells you the timber's in reasonably good condition, and then when you get this red line here, that's indicating where the pocket of decay is, and the algorithm inside the drill does all this for you. I could probably talk for hours about the benefits and disadvantages of both types of methods, but I'm going to swiftly move on. Looking for moisture, important, the correct use of a moisture meter here. So the difference to really understand is, has the building been exposed to just a little bit of wetting due to rainfall, or is it more pernicious? Is the moisture deep within the timber itself? So your uninsulated pins on the surface are going to tell you whether you've just got timber wetting on the surface, on the boundary layer, and that water will quickly flash off if you get some air through the building and a bit of sunshine. More importantly, the readings I like to take are core readings, where I drill into the timber, put in the insulated probes to see what the core moisture content is. So wet on the outside, dry on the inside, not so much of a problem. Dry on the outside, wet on the inside, then you need to think very carefully about what you're going to do. Now, the disadvantage of using this type of survey method is you're going to be drilling quite a lot of holes, and it's quite time consuming. So we've been looking at using ground penetrating radar as a potential method of having a quick first pass through a building. I first used this on Tower Bridge, where we were asked to assess the condition of the panels underneath the road surface. So the site engineers were carrying out core drillings in a random manner, which wasn't particularly very effective. So we thought, if we can tune the radar, we should be able to look for wet patches underneath the road structure. So the way it works is different materials have different dielectric constants, and wet materials have a higher reading than drier materials. And I'm going to move swiftly on to the next slide. Obviously, you do need the skills of a geophysical engineer to interpret it. And the results we got when we scanned the bridge was the red areas show areas of, the red zones show areas of quite intense wetting, and the blue zones show areas where the timber's a lot drier. So we compared this to some lab data. It's good for showing the difference between dry timber and wet timber. It's not sensitive enough to tell the difference between dry timber and slightly damp timber. So you really are looking for substantial wet patches. There are other methods you can use. You could use infrared thermography, for example, to look for cold spots in the building. That might indicate there's some water hanging around. Some remedial strategies. Well, Plan A, and the best way of doing this, is ventilation. Dry the timber out naturally. Construction pathways don't always allow for this, in which case you may have to think about using the diffusible timber preservatives, such as use of boron, which is well established. It's got a good track record, and the actual moisture within the timber does help the penetration of the preservative. Now, drying out a building. It's easy to dry out an open timber frame building, with possible exception of the sole plates. It's difficult to remove water from a wet cross-laminated timber panel. And we do know that if we subject these panels to rapid drying, we can cause the development of internal stresses, disruption of the glue lines, and we can create these water pathways if there's any subsequent wetting. So one way to perhaps protect your cross-laminated timber panels is to carry out a pre-treatment. Now, in Japan, there's an example of an airport in the Southern Islands. I can't remember the name, and I can't read it on that slide. But quite simply, they just get a chap with a squeegee brush and apply a boron-based preservative on the surface, and away you go. And as the pictures show, you get good diffusion. So at this point, I'm now going to pass back to James.
Great, thank you, John. So you've discovered that you've got rotten timber in your building, then what do you do? Well, it's not as bad as you might think. There's quite an easy process that you can follow to actually try and remediate the problem. And it really depends how extensive the decay is and how long it's been left untreated. And the first priority really is to make the structure safe, because as we saw, timber can lose strength. And so if it's not able to support the loads, the main thing that you need to do is make that structure safe. Once you've made it safe, the next priority is really to dry that timber out, because by drying out, you will increase the strength of any residual timber and you will stop that decay process continuing and getting worse. So that's really an essential part of that process. Once the timber's dry, you can actually start to appraise those structural members to understand the loads that are on there and the residual strength of any affected members. And once you know that, then you can devise suitable repair strategies. So in this example, you can see on the image on the left, the bottom corner of a window where the sill has let moisture come through, and you can see the staining and the mold progression in the OSB sheathing there and the path of the water down onto the beam below. And the image on the right shows the beam that's actually supporting that wall panel and the window above it. And you can see my screwdriver pushed right in there up to the end, and it's completely lost in the timber with very little force. So there's not much strength remaining in that timber beam. And it's likely that wall panel is being supported by other load paths. But the first thing really to do is to support that beam and make sure that that wall panel is properly supported and safe. The next thing to do is to dry out those timber elements. And the process to do that really is to stop more moisture getting to those timber elements. You're going to struggle if moisture is still getting to them. And then uncover the timber elements as well. Take off any coverings, and that will allow the natural ventilation process to work quicker. And things like opening windows, as long as you don't allow more moisture in, things like that. And dehumidifiers are very good. They can control the environment and reduce the relative humidity so that will accelerate the drying of the timber. Heating is generally not recommended because you can dry out the sort of external portion of the wood and the timber quicker, and that can distort the elements. And it also poses a fire risk, which nobody wants in a timber building. So once you've dried out the timber, you can start to assess, how much of the structural element is remaining. So in this example, in the photograph, you can see a cast iron component that has been fixed to a timber rafter. And, in high relative humidity conditions, that cast iron foot there is where moisture might condense. And it's also providing a sort of an unventilated zone at that interface between the steel connection and the timber rafter. And so when moisture does get into that interface, then it's very difficult to get it out again. But this is an old building, so it's taken a long time for that decay to really to appear and get to a point where perhaps an intervention might be needed. Again, you can see the trusty screwdriver to try and determine how much of that rafter has been lost to decay. And you can see that drawing that sketch of the cross section on the right, and it's estimated top 50 millimeters of the rafter has been lost to decay. So then you can move on to doing your structural analysis. You can define the loads that the structure is expected to support in service, and you can then define the internal stresses that structural member has to support. And there'll be parts of the structural member that are working hard, the full design capacity, and others that will be working less hard. And so by understanding where the decay is, you can start to build up a picture of what the internal forces are. Once you know the internal forces, you can actually start to calculate how much strength reduction in the timber there's been due to the loss of the section from decay. So in this example, if we've lost 50 millimeters from the top of a 280 millimeter section, you can see the highlighted row in that table there. So we've lost 18% of the section, and we get a linear reduction in the compressive strength of that element. But when we look at things like bending strength and stiffness, the loss is non-linear, so we can lose up to 33% of the bending strength and up to 45% of the residual stiffness, even though we've only lost sort of 18% of the section there. So when we're devising a repair strategy or an intervention, there's a sort of a simple flow chart that you can follow to understand, you know, what level of intervention you need. And so once you've identified decay, know how much of the section you've lost, you've done your structural analysis, then you can ask yourself questions such as, you know, does the structural member still perform as designed? And if the answer is yes, then actually you may not need to do anything. All you need to do is just prevent that moisture getting into the timber again. And as long as you can prevent that, then you should be all right in future. If the answer to that is no, then you can start to do some analysis. And in structural design, there's of course factors of safety. So can the structural member still support the load? If the answer is yes, and you may not be quite at the level of at the factor of safety that the codes and standards require, then it may be suitable to monitor the structure and just keep an eye on it, and that give you the extra level of safety required. And that may be the case for historic buildings. And if the structural member can't support the load, then you're looking at repairs. So the principles for designing repairs, you know, a lot of people are familiar with the historic sort of building principles of repairing, and you know, you can apply those general principles to any type of building really. So the primary thing is just prevent the timber becoming wet again, sort out the original problem that caused it to become wet in the first place, and then only repair as much timber as really necessary, so that you keep as much of the original member as possible, and use similar materials where possible so they have similar characteristics. Another one is to use reversible repairs if possible, so that, you know, in future, if there's modifications or additional repairs that need to be carried out, it's easier to undo them. And sympathetic repairs, again, this is often for historic buildings, but again, you know, it's a good principle to apply to any repair. There's different types of timber repairs, each with their sort of benefits and pros and cons. You can do a timber repair, which is generally quite sympathetic to the original material, but they are often low strength. You can then, if you need more strength, you can start to consider steel plates, but they're obviously visible. And so in some cases, they may not be the preferred choice. And finally, we have adhesive repairs, which are excellent if you need to reinstate the original strength and stiffness, but they do come with the problem that it needs very specialist contractors to actually carry them out, because if they're not installed properly, then they may not achieve the strength that they were supposed to. So here's an example of a timber repair where you're just sort of doubling up the timber and bolting through. It doesn't look very pretty. It can be done a little bit neater than that, but that's just an example of how you might repair a decayed end of a beam or a rafter. And then here's an example of a steel repair. So something that you might choose to do with the rafter and the cast iron casting in the example previously. You may choose to put a steel plate on each side of the rafter and fill the area that was decayed with a new section of timber. And so the steel plate essentially just bypasses that decayed area of the timber. And then here's an example of an adhesive repair. Often when timber members are built into masonry, the end, as I was saying earlier, the end grain is particularly susceptible to moisture. And if you have any moisture in your masonry wall, then that can migrate into the timber and cause decay over time. And so it's a common repair to replace the ends of beams. And you can do that with adhesives by, similar to reinforced concrete, where you put some reinforcing bar and attach it to the timber. And you can either put in a new piece of timber, or you can use the adhesive to form the end of the beam. So in the photograph, in the example below, you just pour in the timber bit into some formwork, wait for the adhesive to cure, and then you've got a new beam end, but not reversible. You end up having to cut out more than you started with. Okay, so here's a case study of CLT. A lot of people are concerned that CLT is not easily repaired, whereas in actual fact, if you understand the material and you understand the problem and what the decay has done and the function of the CLT, you can use similar repair methods to fix CLT slabs as well. So this is an example of where you've got decay in the top layer of a CLT panel. And, you know, if the decay is minimal, you may decide that actually the CLT has enough residual strength that you don't need to do anything other than maybe fill that pocket of decay and stop the moisture getting in again. But if the decay is more extensive, you may choose to fill that top layer. And you can see in the diagram below that you just insert a new piece of timber and then stitch it to the original CLT panel using carbon fiber plates bonded in place. And here's a photograph showing that repair that was successfully carried out. On the left-hand side, you can see the original CLT floor panel. On the right-hand side, you can see just standard sawn timber, which is the same material as the CLT, and it's all bonded into place and then stitched back using those carbon fiber plates. In the case where the decay is maybe more extensive or deeper into the CLT than is considered to be acceptable just to replace the top layer, then in some cases you may need to do a full depth repair. And when you're in an existing building, you may have limitations on the size of the members that you can actually install. So this is an example where you could bring in sort of 2 elements to actually span the full width of the floor. And this is using glulam that's attached to the existing CLT structure and then stitched back together, and using steel brackets at the end to fix it all back together. And here's the photo showing the completed repair. Some of the photos shown earlier were images of how bad that CLT floor panel were in the first instance. But now we can see here with the glulam elements, it's almost back to how it was originally. You know, uncovering that, you wouldn't see much difference between the original CLT and the glulam, other than the area that it's been stitched back together using those carbon fiber plates bonded in place. So in conclusion, the primary message, the take-home message for today is, you know, really try to stop timber getting wet. Keep that moisture out. Do everything that you can to stop the timber getting wet. And if it does get wet, dry it out before it does any damage. You know, timber can cope with wetting for a short period of time, but if you don't dry it out within a reasonable time frame, then you can get decay, and then it becomes much more of a problem. When you've just finished building a building, check for that construction moisture before closing up. And if you are concerned about moisture getting in, then you can manage that risk by providing ventilation or by treating the timber. And as soon as you observe any moisture damage, make sure that you act before it becomes a problem. So really, if there is any evidence of moisture, act quickly. And if you are concerned, there's a range of non-destructive investigation methods that you can use to identify moisture, and use those to target any opening up works, because obviously the opening up works are costly. So you want to be quite targeted of where you do those. And then use your structural analysis to understand the cause and the possible effects of the decay, and then use that to determine your appropriate intervention strategy. And then there's a whole series of repair strategies that you can employ to remediate your building. And so on that note, I'll move on to the last slide. And so tell you all a big thank you for listening and giving us your time this morning. And we'll move on to questions.
Yeah, well, here, thanks, guys. That was a great presentation. One of the particular areas I have to say that did catch my attention was the toys, especially the ground penetrating radar, and I can't quite remember the precise name for it, but it was the pressure measuring drill. Now, I know at the PCA we are constantly trying to understand and embrace new emerging technology. Can you guys see wide adoption of this? And if so, what do we need to do to prepare for it? What sort of protocols and potential standards do we need to bring in if we are going to consider bringing in toys like this?
I think with the mechanical drills, it takes away the subjectivity of the assessors. So an experienced surveyor, I think it should be reasonably comfortable of using a probe in a standard hand drill. But I think if you've got less experience, these mechanical drills do take out quite a lot of doubt. And the other thing is also there's a digital record of your drilling procedures. So all that information can be held in a library, particularly a library of data, particularly if you're dealing with a large public building, for example. It's just a way of taking out assessor subjectivity. So if you have a team of 4 surveyors inspecting the same buildings, then if they use the same drill, they're going to get the same results as opposed to that variation. And with reference to the ground penetrating radar, when I used this on Tower Bridge, I was quite surprised at just how informative it was. I think it does have a use in larger mass timber buildings because it will refine the search rather than drilling numerous holes. You can certainly reduce the amount of damage. It'll be a lot more focused. Sorry.
No, on you go. Sorry, I thought you were finished there. No, but I kind of get where you're coming from. That's the geekiness in me, I suppose, when I saw the toys and I saw the results and I saw the graphs that you were coming from. It really kind of sparked, it really caught my attention, I suppose. But I'm really keen to go into questions here because we do have quite a lot of questions that have come through both prior to the webinar starting via email and over the course of the webinar. So the only thing I would maybe ask, guys, and I know this is difficult, but speed up going through if you can make the answers as quick and as short as possible. But I'm going to start off with a controversial one, and it's maybe one that's that you both want to kind of get into. This one comes from May Anderson. Now, over the course of the presentation, you mentioned that wood destroying insects are rarely a problem, but with global warming featuring daily in headlines, do you think we should design timber buildings with the risk of termite infestations in mind? And if so, how? What would you propose?
Well, I'd probably adopt the Home Office policy here of keeping out undesirable aliens.
Well, that was a short answer. But James, what do you think?
I think, it's hard to tell how the climate is going to change. As John showed in his slide, actually the climate is likely to get wetter, so we need to make sure that our buildings are more resilient, and we just follow the same sort of design principles that actually we keep the timber dry. That's our best defense against sort of any kind of insect. So if we do get some sort of new insects that we're not familiar with up until now, then I think we keep designing for natural durability, and we don't sort of over design on a possibility that might occur, because there's a balance that we want to be resource efficient with what we're doing, and so we shouldn't over design on the possibility that something might occur, and if it does occur in the future, we'll have to deal with it.
Okay, well, I think that nicely leads on to a question that came from Carl Stevens, which is all about durability and right woods. Carl was asking, is there any, well, this is referring to the white woods that you are, I believe it was yourself, John, that was talking about, but he's asking, is there any evidence that homegrown whitewood framing is less durable than the same timber species grown in Nordic, Baltic countries? If so, do you attribute this to lower wood density or higher sap content? I'm not quite sure of the latter, but I'm not, but maybe hopefully you guys will be able to answer that.
That's a whole conference worth of information in that
Is it?
question.
Wow.
The short answer is a lot of work has been done by the Centre of Timber Engineering in Napier, which debunks the myth that homegrown whitewood is inferior to imported whitewood in terms of its use for structural framing. There is perception that homegrown wood is of lower quality. Yeah, true, we do have faster rates of growth and the wood can be more knotty. In terms of its durability, the sapwood of both species has no resistance to decay. The relevant standards you go to, which I think is BSEN 942, describes European whitewood and UK whitewood as both having the same, the heartwood as having low durability. However, if you go to other publications, you can find, if you go to the Trada species handbook, homegrown whitewood, Sitka spruce, and a mixture of fir is described as having no resistance to decay, the heartwood. But in reality, if you're dealing with something which is low durability and something which is no durability, that's not an awful lot in it. If they both get wet, they're both going to rot. So keep the water out.
Well, you've led nicely again onto a question that's actually probably the most common question that I've had both via social, email, and on the chat in itself. And it actually alludes to how much is a little bit of wetting? Can this be quantified? But on top of that as well, for joint question, I'm conscious of time. Firstly, how much is a little bit of wetting, and also how long would a prolonged period of exposure of wetting need to be before rot really kicks in? Now, I know to a certain degree this is a finger in the air, and how long is a piece of string? Is there any sort of quick guide tips that you might be able to give out?
Okay, I'll try and do this as briefly as possible. If it's days or a couple of weeks, it probably isn't going to be a problem. There will be exceptions to that. If you're dealing with months up to years, then you need to be really, really very careful. And the best way to really get a handle on this is using your inspection tools. So going back to the moisture meter, if the outside is wet and the core is dry, then you probably haven't got too much of a problem. If it's the reverse with the core being wet, then you really need to think very carefully about what you're doing, because not only do you have a decay risk, you've also got a fixity problem and perhaps a strength problem. So if it does decay, you've got double problems there. Yeah, it says that this is a how long is a piece of string type of question. That is my view, very briefly. Highly qualified by the time I've been allowed to I've given to it. And James, do you have a view?
Yeah, I think again, it's a very difficult question to answer because it really does depend on a lot of factors. One of those factors is the type of timber that you're using. You know, solid timbers tend to be more or less susceptible than perhaps some of the thinner plywoods, OSB type materials. But it also depends on your actions and how you intervene in that process. And so during construction, you can get significant amounts of water, as John showed in some of his pictures. But, you know, there's quite simple intervention strategies that you can do to actually remove that moisture. Just so getting rid of that moisture, protecting the structure if you've got sort of the potential for heavy rain forecast over that construction phase, because typically that construction phase isn't that long until you get the roof on. But then in service, if you've got moisture, then it's usually a defect. So the quicker that you can identify that defect, the quicker that you can intervene, the better. And, you know, if it's a drip that you might not notice, it usually does come out somewhere, and it's listening to, if you're managing a building, then it's listening to your residents to say, we've got a little bit of moisture here, and it's taking those concerns seriously and acting quickly that will be most apparent, rather than sort of saying, oh, I've got a few weeks or a few months before I need to do anything.
No. Yeah, folks, just for everyone listening, I just want to let you know we are running a couple of minutes over. Hopefully many of you can actually stay with us. I am going to try and rattle through as many questions as I can. I'm not going to get through all of them, so I will try and group the questions together as best I can. But I will pass on all your questions over to John and James. I'm not going to make any promises to them, but if they can get back to you for the ones that we've not been able to answer, then hopefully they can. But kind of moving on to the next question. Next one comes from Jason Burstow. This is focusing on repair strategies. He's mentioning that we spoke a lot about measuring the strength of timber, but he's asking, what about the loss of strength in the connections? How can this be measured?
Again, I mean, the connections are often a weak point because, you know, they are typically steel, and so that will attract moisture, and it also creates points where if you do get moisture into those connections, then you struggle to actually release that moisture again and dry it out. So the connections are a weak point, but it's similar kind of processes again, that if you know, your connections rely on affixing into the timber. If the underlying timber has decayed, then you need to replace that timber, and it's about trying to reinstate that that timber in a way that replicates the original design. It's difficult without giving specific examples, but yeah, the connections are a weak point. But again, it is about replacing that timber so that it's back to its original strength if it's decayed.
Well, if I stick on this theme about kind of repairs, John Lee Falcon, he's actually raised a probably a question many of our listeners are maybe kind of thinking about here when it comes to repair or replace. Is there a disproportionate cost to repair compared to maybe using manufactured or potentially common construction methods to actually replace it, especially if it's just new, it's brand new timber, it's been brand new framed, it's been wetted? Is it just easier just to cut the whole thing out, replace the whole section?
It can be. It really depends how extensive your decay is, and so, you know, that's really a costing exercise. And, you know, we'd like to try and limit the amount of timber we replace, because we need to be sort of efficient with our resources. But yeah, it can be to the point where the timber is so badly decayed that it's easier just to replace an element. But that can be quite difficult in itself, because if it's, you know, a wall stud or a sole plate or something like that, can be quite difficult to repair. You could replace a stud quite easily because there's lots of other members, whereas if you've got a beam that is sort of responsible for holding a significant portion of the structure up, it might be more costly in temporary works to actually support the rest of the building to allow you to replace that element. And sometimes if you've got an existing building, the element is bigger than the size of the room, so you can't actually get it in. So you need sort of new elements in there, and sort of you need connections where previously you didn't have them, and things like that. So again, it really depends on the type of building and the type of repair and damage that you have.
Well, here, folks, John, James, many thanks there. We have not been able to get through all the questions, folks. As I said, I will pass over those questions over to both John and James, and if they can get back to you, I'm not making any promises, but if they can get back to you, then great stuff. Just to kind of let you know, if you are looking for additional information, there is a variety of documents just up there that you can look up, starting off with their own PCA technical library. There's codes of practice up there and guidance notes. You can also go to the Structural Timber Association site, where there's a document about the robustness of CLT, cross-laminated timber structures. TRADA also has some supporting information there as well. And ICA, that's the Engineering Knowledge Library, also has an appraisal and repair of timber structures document that's worthwhile taking a wee look. There is also the recording of this webinar, which should be available later on. I've got next week there, that's been a typo, but it should be available from tomorrow at some point, that you can look over again and share out with any of your colleagues. In case you are interested, there is some training courses that if you so chose to do so and you want to gain a little bit more knowledge, you can do. If I start off with our timber and dampness and buildings training course, it's now both online as well as classroom based. The online version is relatively new. It is there for your convenience. There's 10 live sessions, there's 12 recorded videos, 6 interactive sessions, and multiple professional trainers. If you're interested, go to the website to find out more. But more maybe towards a lot of you here, there is the wood identification course. I will warn you, this is quite intense, but it is a real one-day masterclass. And if you've got any kind of hands-on guys dealing with repairs, there is some technical training and also training in terms of the safe use of biocides for professional users. Just a little bit about next webinar. Next month, we now switch and we start to look at the structural waterproofing industry, in particular, the brand new BSI 8102 update. Does this change our view towards waterproofing? Mark your calendars for that. It's on Thursday, the 28th of April, and we do hope we see many of you there. Lastly, but not least, I just want to say, firstly, a big thank you to everyone that tuned in today and taking the time out to listen to what we have to say. I want to say a special big thank you to both John and James for the great jointly presented presentation today. And lastly, I just want to say and bid you everyone a farewell, and hopefully you all have a lovely rest of the day. Goodbye, everyone, and hopefully we see you next time.
Bye.